Hello, everyone, and welcome to our Capstone presentation.
I'm Fredrick Fox.
I'm Nicklaus Garces, and today we're presenting an artificial neural network optimization with gradient descent.
We'd like to thank Yadrin and from our Capstone advisor and Dr. Quinn for organizing all the senior Capstone presentations.
Let's begin with the outline. First, our introduction will cover what is machine learning, what are neural networks, and how are they used. And then we're going to go into forward and back propagation with gradient descent. And this is how we move data through a neural network and how we improve performance. And then we're going to finish out with our numerical experiments and our conclusions based on image classification with Keras datasets that we did and TensorFlow. So introduction, what is machine learning? What is a neural network and how are they used? What is machine learning? Machine learning is a scientific study of algorithms, statistical models that computer systems use to perform a specific task without using explicit instructions, relying on patterns and inference instead. So suppose I give our neural network a picture of a shoe. I want it to be able to make patterns and inferences based on the shape of the shoe to classify as a shoe, but I'm going to do that by letting it do it by itself without giving it explicit instructions. But we're going to help it by giving it training data to help the artificial intelligence make the inferences. So what are artificial neural networks and how are they used? Artificial neural networks are brain-inspired systems which are intended to replicate the way that we humans learn. So on the top right is an image of a web of neurons in the human brain, and the bottom right is an artificial neural network. In the image of the human brain, there's a web that connects the neurons. We're going to replicate this with layers and connections between the neurons and the layers. So input layer has connections to hidden layer 1 with these little lines that we'll call weights. We're going to use the AI to predict outcomes given information. And some examples uses of this are image classification, facial recognition, autocorrection, motion detection, and many more. So in this GIF on the left, we're going to be inputting the 7 into our input layer, and then we're going to move this data forward and then arrive at the output layer where we classify it as a 7. This is called forward propagation. We're propagating our data forward. And now we're going to know how is data processed through a neural network. So suppose we want to input this 28 by 28 pixel image of a shoe into our neural network. How do we feed it in? Because we don't care about the color, we only care about the shape, we're going to grayscale this to assign each pixel a value between 0 and 255. And then we're going to put each pixel value into a 784 row vector. It's rows because that's just how we're going to orientate our neural network. So here's our input layer. It's a vector with 784 rows. H0 equals H0 sub 1, H0 sub 2, H0 sub 784, where 784 is the amount of neurons we have in this layer. And the superscript denotes the layer we're in. So since we're in the initial layer, we would call it layer 0. And if you look at the image in the bottom right, we have that the input layer equals x0 sub 1, x0 sub 2. We're just going to change x0 to equal h0 for notational purposes. So then we can generalize this input layer to a vector with I rows, where I is the amount of neurons, and we're using it to be HL minus 1 equals HL minus 1 sub 1, HL minus 2 sub 2, HL minus 1 sub I. And we're going to use HL minus 1 to calculate for HL. So in this hidden layer, these hidden layers are the layers after the input layer and before our output layer. And the forward propagation process is we want to go from the input layer to the output layer. But first we have to go through the hidden layers. So in this example, we have to go through hidden layer 1, and we're going to use the input layer to calculate for hidden layer 1, and then use hidden layer 1 to calculate for the output layer. So onto the weights. So how I like to think of it is like, if I have a picture of a bird, there are certain things that make a bird a bird. So in my head, the wings hold a very big significance to making something a bird. So let's say it has a 50% significance. That's its connection from the input, my input of a bird in my head, to an output of knowing that it's a bird. And we're going to call this significance a weight. And weights connect all the layers, layer L and L minus 1. So in this image, we have weights between the input layer and hidden layer 1 and hidden layer 1 to the output layer. So we're going to expand the weights to be a K by I matrix where it's WL KI, where I is the amount of neurons in layer L minus 1 and K is the amount of neurons in layer L. So then we're going to multiply this by HL minus 1, and this will result in a K by 1 vector. So next is the bias. The bias is known as the activation threshold. What this means, as an example, is like if I were to poke you with a pencil and increase the speed slowly over time, eventually it'll be meaningful in your head and be considered pain. This meaningfulness is what the activation threshold is. We want to make sure that WL times HL minus 1 is high enough to be counted as meaningful. So that's why we're going to add this to WL times HL minus 1. Next is our activation function. This function will tell us how activated our neurons are. The activation function we will use is called the sigmoid function, where it's sigmoid of x equals 1 over 1 plus e to the negative x. And we're going to apply this to WL times HL minus 1 plus BL, which we will refer to now as ZL, just to shorten the notation. And this function is nice because it squishes all inputs to an output between 0 and 1. So if it's 0, then it's not activated. If it's 1, it's activated. So the closer they are, the closer to being non-activated or activated. So some things to note about the activation function. Our activation function must be nonlinear to add nonlinearity to our neural network. Because if we use a linear function or a nonlinear activation function, then since we're only doing multiplication and addition multiple times, we could just condense it down to doing it once. Then we'd only have an input layer and output layer. But we need the multiple layers to be able to make a lot of inferences. And linear activation functions cannot be used for backpropagation. TLDR, it's because we can't take multiple derivatives of linear functions. So then calculate for the next hidden layer's neurons. So for example, if we were trying to calculate for hidden layer 1's neurons, we would do W1 times H0 plus B1, and that would be equal to sigmoid of Z1, and that would give us H1. So then to generalize it for all, because we have to go from every single hidden layer to every single other hidden layer forward after it, sigmoid of WL times HL minus 1 plus BL equals sigma of ZL equals HL. And we're going to do this L times since our neural network has L layers. And the last layer we would denote as capital L. So then question, how do we get our weights and biases for the whole neural network? We're actually going to initialize them randomly, and essentially this will give us like a 0% accuracy, but then we're going to use a process called gradient descent to change them in a way that gives us better accuracy.
So now we'll talk about gradient descent with backpropagation. We'll discuss how to determine if our network is performing well, what is gradient descent, what is backpropagation, why is it needed. So to start, we'll look at cost functions. Cost functions give us insight in how well a network is performing by giving us a numerical value of how wrong our prediction is. To where for our capstone, we focus solely on the mean squared error metric as our cost function, to where y and y had to note the predicted value versus the expected value of a training example. So now we have a cost function. We want to find the parameters that minimize this cost. If we have a larger cost, we have a lower accuracy. If we have a lower cost, we have a higher accuracy. So to optimize this cost function, we will use gradient descent. Gradient descent is an optimization algorithm for finding local minima. The gradient descent uses the gradient as an indicator of how far away we are from a local minima. If we have a large gradient, then we are not close to a local minima. If we have a low gradient, we are close to a local minima or at that local minima. Gradient descent uses an update rule to update our parameters based on the O parameter with the sum of the partial derivative with respect to that parameter times a learning rate lambda. So neural networks are complex structures. How do we obtain these partial derivatives with respect to a weight or a bias? We use backpropagation to remedy this. So backpropagation looks at the effects each neuron has on the performance of subsequent layers. The performance of a neuron will give us insight in how we should update the parameters associated with it, namely the weights and biases, to improve performance. We'll denote the error of a neuron as delta L sub j, to where this is a partial of the cost function with respect to the input of the jth neuron of the lth layer. If we expand this and vectorize this for the whole layer, we'll see that our error is related to the error of subsequent layers. So if we minimize the error of previous layers, this will increase our performance of the subsequent layers and then our output, which will yield a higher accuracy and a lower cost. So since we want to use gradient descent, we will use the same update rule that gradient descent has laid out for us. With the error that we have defined before, we can derive the partials with respect to the parameters in terms of that error. So with gradient descent, we will update each of these parameters based on the O parameter plus the partial with respect to that parameter times the learning rate lambda. We will do this iteratively until we arrive at parameters that minimize the cost function throughout our training set. So with our capstone, we did numerical experiments with 3 different data sets that Carousel allowed us to use: MNIST fashion, MNIST handwriting, and the CIFR-10. We focused mostly on the MNIST fashion data set, which gave us 60,000 training images, 10,000 test images. Where these are some example images that we had to work with, where we had many different types of pants, shoes, shirts, dresses, 10 different types of clothing. So we set up our own neural network, which, as we said before, had an input layer length of 784 neurons, one hidden layer of 120 neurons, an output layer of 10 with the 10 labels of the data set. Both of these layers had activated function of sigmoid. We used a learning rate of 0.5. We gave our network 6 training sessions with 60,000 images, 10,000 images per training session. So we took a sample of 15 test images and we had our network evaluate them. We can see for most of these images, our network was able to confidently guess the correct label for these clothing items. However, we see in the bottom left-hand corner that our network confidently categorized a sneaker as a sandal. Even though this is wrong, this is a good sign that our data is not overfitted. Our neural network was still able to classify this piece of footwear as a piece of footwear, not as a dress or a shirt. It was still able to categorize this thing based on its shape. We can expand on this idea further by looking at the confusion matrix. This matrix gives us every single correct and incorrect prediction our network had over the 10,000 test images, where we can see if we look at a sneaker, our network never categorized as any other type of clothing that was not a piece of footwear, or not a piece of footwear. It only had discrepancies with other types of footwear and apparently a bag. Whereas if we look at a coat or as a coat, we can see that there's a lot of discrepancies with other types of clothing, such as a pullover, a dress, and a shirt. But however, the same trend can be seen that it never classified this piece of clothing as a piece of footwear. So our network is able to categorize these images based on their shape. The details do not necessarily matter, but each of these images have unique shapes. So we also wanted to see what the effect of the learning rate had on our accuracy and our training. So we chose 2 other extreme learning rates, 100 and 0.01, along with our 0.5 learning rate. And we compared the accuracies. We can see that our learning that we chose initially was far better. We had accuracy of about 80%, whereas other accuracies were around 35% or less. This is due to gradient descent being very sensitive to the learning rate. A large learning rate causes a lot of oscillation when we are trying to converge to local minima, which will cause us not to converge. However, a low learning rate will cause us to converge to a local minima, but at a very slow rate, which under 6 training sessions, we were not able to converge to that local minima. So we also want to see if this architecture that we made was suitable for other types of data sets. We trained this data set we trained this neural network on 3 different data sets: the MNIST fashion, the MNIST handwriting, and the CIFR-10. The CIFR-10 had different categories of automobile, bird, cat, deer, horse. These images had a lot more detail to them, so our network was not able to pick up on all these details. It was only able to pick up on the generic shapes of them, where we can see that the accuracy in the MNIST data sets was much higher, since these images are able to be categorized based solely on their shape. Whereas CIFR-10, there's many different details that can distinguish a deer from a horse or a dog from a cat. And now we will discuss overfitting.
So the last thing we had to consider was overfitting, is where we reduce our cost to 0, where we reduce our error to 0 based on the training set. But by doing that, if we reduce our error to 0 on the training set, that means we're gonna also, like when we input new test data, it's gonna perform poorly because it was only fitted to the training data. We decided that our neural network was not overfitted if the accuracy on the training data was similar to the accuracy on the test data. So for example, our accuracy of 80% was accuracy of 80% on the training data, and also accuracy of 80% on the test data. Thank you for listening. Do we have any questions?